All right, so on this video, we're going to talk about graphing sines and cosine functions with transformations relating to the x values. On the previous video, and you should go back and watch that before this one, we talked about graphing sine and cosine with changes in amplitude and vertical shifts. Those would be transformations that affect the y values. So we're going to start by graphing y equals sine of 2x. And you may recall from earlier discussions on graphing functions, the only difference now is we've doubled the x, we've put a 2 right next to the x, and if you recall, that's actually going to cause a horizontal, it's opposite of what you would think. It's not going to stretch your x values out, it's going to compress your x values. I thought to really see this, what I'm going to do is just go ahead and graph regular sine of x in pink here. So remember, regular sine of x, you should be able to recreate that graph pretty easily now without any assistance. A regular sine graph starts at middle, which is 0, pi over 2 is high, middle, low, back to middle. So here is regular sine of x. And you can kind of see then, like, for example, we know the sine of pi over 2 is 1, but what would make sine of 2x equal to pi over 2 would actually be pi over 4, half of that value. So sine of 2x is going to reach its peak at pi over 4 rather than pi over 2, because you're going to double it, and that's when it's going to be at its high. At pi over 2, if you put that in and double it, that's actually going to be pi, and the sine of pi is 0. So it's actually going to be back at its middle. And you can kind of see, hopefully now, if you think about it in terms of symmetry, middle, high, middle, the next time it's going to be at low is halfway between pi over 2 and pi. And then it's going to be back to its middle. So one complete period of sine of 2x happens just between 0 and 2 pi. And then you can really see it's like taking the regular sine graph and compressing it together so that it finishes one cycle between 0 and pi rather than 0 and 2 pi. This is this graph right here. So you know that we've recognized that as a horizontal compression. For the purposes of sine and cosine graphs, when you shrink a graph this way, you're affecting the period. And so another way to describe that horizontal compression is it's going to affect the period. The normal period of a sine graph is 2 pi, but now it's going to be cut in half because of that horizontal compression, which means it's just going to be pi. And we can see that right here. So any number times x on the inside of a sine or a cosine graph is going to affect the period. Okay, next one, let's practice this. Y equals 5 cosine. Here, let's see one actually. Let's make this 1/3 x, just so we can see the opposite effect, where now, let's go ahead and talk about this right now. This is going to actually cause a horizontal stretch of our graph, and it's going to affect the period, and I can find my new period the same way. I can take my normal period of a cosine graph, divide it by that coefficient 1/3, and that actually gives me 6 pi. So this 1/3 is causing a horizontal stretch by a factor of 3. Okay, the other transformations we talked about on the previous video, this plus 6 is going to move our graph up 6. So our new middle, instead of being 0, it's going to be 6, and this 5 is going to affect my amplitude. So sketching this, just get a rough sketch. Let's sort out our y values first. Our new middle is going to be 6 because our whole graph is up 6. Amplitude is 5, so from our middle, that means we can go up to a high of 11 and down to a low of 1. We're just adding 5, subtracting 5. The period now is going to be 6 pi, but it still has a cosine or a sine graph, still has 4 parts to it, so we're still starting at 0. We're going to finish this at 6 pi, but we now have to figure out what these new quarter points are on our cosine graph. There's a couple ways you can do this. One way to do it is you can take the normal places, like normally we associate this with pi over 2, but if it's been stretched by a factor of 3, we just multiply that pi over 2 by 3. Another way to do it, and this is probably the way I usually prefer to do it, is by thinking of a sine or a cosine graph in fourths. If I take 1/4 of this period, meaning 1/4 of 6 pi, that gives me 3 pi over 2 if I reduce it. So then I can just picture counting by 3 pi over 2's. So if I start at 0, this first point is 3 pi over 2. If I add another 3 pi over 2, I get 6 pi over 2, which is 3 pi. Add another 3 pi over 2 to 6 pi over 2, that gives me 9 pi over 2. And if I do that again, I get 12 pi over 2, which is 6 pi. Okay, so I know it's a cosine graph. It's going to start at its high, then it goes to middle, low, middle, back to high. Something like that. Okay. Now another transformation that we can do that affects the x values, and this one's maybe more familiar, you've seen this before. If we, instead of multiplying x by something, we do something like x minus pi over 6, you should recognize that as a horizontal shift from earlier graphing we've done. This is going to move my whole graph right by pi over 6. My amplitude is 3, and that's it in terms of the transformations. But if it's moving my whole graph right by pi over 6, what that means is instead of starting at 0, we're going to start our graph actually at pi over 6, meaning at pi over 6 is where it's going to be at. Normally sine starts at the middle. Let's get our high. Our high is going to be 3. This is our middle because it hasn't been raised up or down. And our low would be -3 since our amplitude's 3. Now there's still, let's go ahead and sketch our graph. There's going to be 4 parts to this sine graph. We know a sine starts at the middle, then goes high, back to middle, low, back to middle. So we've got our graph. A lot of times to get full credit, what you're going to want is you're going to want values for each of these x components, these x places on the x-axis. So we can do that the same way as I did the previous one. The distance between each hash mark here is 1/4 of the period. My period, since there wasn't any coefficient in front of x, my normal period is 2 pi. So I'm going to take 1/4 of 2 pi. That's 2 pi over 4 or pi over 2. And what I want to do then, that means I'm just going to be adding pi over 2, but now I'm starting from pi over 6. So if I'm going to add pi over 2 to pi over 6, it's convenient to go ahead and give it a common denominator and think of pi over 2 as 3 pi over 6. Then I can just add 3 pi over 6. We can reduce this later. That would be 4 pi over 6. If I add another 3 pi over 6, I get 7 pi over 6. Add another 3 pi over 6, I get 10 pi over 6. One more, I finish off at 13 pi over 6. Of course, these middle ones reduce. That's 2 pi over 3. 10 pi over 6 reduces to 5 pi over 3. And let's do one more. This one kind of has everything. We've got, it's a cosine graph. We've got an amplitude of 2. We know this graph has moved up 4. Now, we've talked about both of the 3 and the pi both affect what we've just been talking about, meaning it's going to affect the period and there's going to be a horizontal shift. You have to be a little bit careful though. It looks like the graph's been shifted over by pi, but it's not really that. So one way to see the horizontal shift is if I rewrite this graph as y equals 2 cosine and I factor out 3 from 3x minus pi, that is going to make that 3 times quantity x minus pi over 3. And we can actually see that the graph has in fact been shifted to the right by pi over 3. And this 3 is going to affect our period. It's going to take our normal period of 2 pi and divide it by 3. It's a horizontal compression. So you can do that. You can, if you see it written like this, you can either factor out the number and figure out what your actual horizontal translation is. Another way to do it, you can figure out that it's been shifted to the right by pi over 3 if you just set this equal to 0. If I set 3x minus pi equal to 0, that gives me x equals pi over 3. And I can interpret that as my horizontal shift. And then I can take the coefficient of 3 and know that that's going to take my period and divide it by 3. So either way, you can rewrite it or you can just work with this and set it equal to 0. Okay, as far as graphing this, we'll start with the fact that it's up 4. That's my middle. My amplitude is 2, so I can go down as far as 2 and up as high as 6. I'm starting my graph not at 0, but right at pi over 3. And it's going to have 4 parts to this, so we'll divide it into 4 pieces. I always tell students, if this is a test, everything's worth points, including the graph. So the hardest part is usually finding out what all of these points are. So if you're going for maximum credit, you're not sure you can get these in time, let's draw the graph first. It's a cosine graph. So where we're starting it, which is at pi over 3, it's going to be high, middle, low, middle, back to high. So now you've got your graph, that's worth points. And to get final credit here, we need to locate these other points here. So as I'm going to stick with what I did before, I'm going to keep adding 1/4 of the period to get to all of these points here. So 1/4 of the period is 1/4 of 2 pi over 3, which is 2 pi over 12, which is pi over 6. So I want to add pi over 6 to pi over 3. So let's think of this in terms of, maybe this time I need to think of pi over 3 in terms of 6. Pi over 3 is really 2 pi over 6. So if I add pi over 6 is what I'm going to be adding to 2 pi over 6. This first point is going to be 3 pi over 6. We can reduce that later. 4 pi over 6. I'm just adding pi over 6. 5 pi over 6. And finally 6 pi over 6, which is of course pi. This is 2 pi over 3. And this reduces to pi over 2. We've got all our points. Right. Planning to do another video after this where another skill to be able to do here, we've been working from the equation and drawing the graph. If you really understand all of this, you should be able to do it the opposite way, meaning I give you a picture of the graph and you have to come up with the equation. So be prepared to do that. I'm going to try to make a video on that as well.